Hi everyone, welcome to this video. We are looking at question number 12. We are continuing with the series of examples we are looking at from the FAMS sample questions. Okay, you can access the questions on the SOA website, and you can also see the solutions that they've provided. Meanwhile, let's take a look at the question here, number 12. You're given the following information about a general liability book of business comprised of 2,500 insureds, and they've given you some information here. XI, we're looking at the summation of YIJ, yeah, and you can read those things yourself, right? We're going from J, going from 1 to NI, and so on. It's a random variable representing the annual loss of the ith insured. Okay, so take note of the important facts, right? So ith insured here, this is how they're defined: XI, N1 right up to N2500. They are independent and identically distributed random variables following a negative binomial distribution with parameters R is 2 and beta is 0.2. Great. And then they give me all these facts here. We have got all the Y's, right? All the Y's are independent. Okay, all the Y's are independent and identically distributed random variables following a Pareto with alpha equals to 3 and theta is 1000. So take note of how XI is defined. Okay, it's telling you something about a random variable representing the annual loss of the ith insured. And take note of this N1 to N2500. And take note of the binomial, negative binomial distribution parameters. Take note of the Y's. They're independent and identically distributed random variables from the Pareto family with alpha is 3 and theta is 1000. The full credibility standard is to be within 5%. So you know the value of R. Good. And of the expected aggregate losses, 90% of the time. And the full credibility standard is to be within 5% of the expected aggregate losses, 90% of the time. Okay, so you know you know what numbers you're going to get from here, right? So I have spoken about that when you have the 5% thing and you have 90% thing. So you know it's going to be like 1082, right? Remember 1082, the famous numbers for us. Okay, for lambda naught. Anyway, I'll remind you of that in a second. Let's see what they want, right? You're asked to calculate the partial credibility, right? Calculate the partial credibility of the annual loss experience for this book of business using limited fluctuation credibility theory. Okay, we're looking for the partial credibility factor. Okay, so what did I write down? What do we need first? Yeah, what are we going to find? Okay, so what are we going to find? So Z will be equals to, we have said, we have seen this formula in my class. Z is the square root of the actual expected number of claims divided by the required expected number of claims. Basically, it's actual over required, right? Z equals to the square root of the actual expected number of claims divided by the required expected number of claims. Now, the actual is pretty easy, right? The actual is pretty easy because how many people do we have? 2,500. So let me look at that. Actual expected will be 2,500 times. We are looking at R is 2 and beta is 0.2. So the expected value will be R beta, remember, from negative binomial. So R beta multiplied by 2,500, right? Plug in the numbers and you will get this number here, which is 1,000. Okay, let me just clear that so you can see the numbers clearly. Okay, 1,000. Done. We're done with that part. Now what we need is the required expected number of claims. That we need to do a little bit of work. So what I did in my solution, I went ahead and found the things that I need to plug into this line here. I covered this in my class. Okay, the required expected, right? The required expected will be bigger than or equals to lambda naught. Lambda naught is easy, yeah. I've done it here for you. It's 1.645 divided by 0.05, all things squared, you'll get 1082.41, yeah. Many of us have memorized this number, 1082.41. Okay, so that's easy. So required expected bigger than or equals to lambda naught times sigma y squared, mu y squared, okay? We have sigma y squared, mu y squared plus sigma n squared over mu n. And there's some derivation here. Okay, we start at some point and we end up here. I went straight to this line here because I'm trying to solve this problem, right? So you can go ahead and look up your lecture notes or something and you'll see this, right? So I need to get values for all of these things. So that's what I've done here. The expected value of y, because I know y is Pareto, right? They told me y is Pareto alpha 3 and theta is 1000. So I 1000 over 3 minus 1, I'll get 500. The expected value of y squared, look this up in your tables, right? 2 theta squared over alpha minus 1 and alpha minus 2. That's in the denominator. So plug in 2 times 1000 squared over 3 minus 1 and 3 minus 2. You get 1000 squared. Great. So the variance of y, just take the second moments minus your first moment squared, and you will get this number here. Expected value of n, we know r beta, 0.4. The variance of n, we also know, okay? We've got r beta times 1 plus beta. Remember, r is 2 and beta is 0.2. So 1 plus beta will be 1.2. So use your calculator if you like, but this you can do it mentally, you'll get 0.48. So all we have to do is just what? Plug in, right? Plug in and you'll get, okay, let's see. Let me move the screen up, right? Okay, so when you plug those numbers in, okay, the required expected will be bigger than or equals to lambda naught, we know. Plug in sigma y squared, mu y squared, all done for you. Sigma n squared, mu n, use a calculator and you'll get bigger than or equals to 4546.122. Okay, so let me clear this. And so the value of z will be the square root of the actual expected over a required expected. So actual expected, we worked out 1000. Required expected, we just worked it out. Use your calculator and you'll get 0.469. Okay, and your correct answer will be C, 0.47. Thank you very much for watching. See you in the next video.